In this video, we're going to be practicing using our trig identities to both simplify and prove some trig expressions. We're going to do a couple problems here. Let's look at number 7. Sine of theta times tangent of 90 degrees minus theta. The idea being here is what can we really simplify? Well, sine of theta, you cannot really do much with that, so we're going to leave that alone. But we do see that tangent of 90 minus theta. We know that there's a property held to that. We know that that is a co-function relationship, and that's really the same thing as a cotangent of theta. So we have sine theta times cotangent theta, and if you really want to simplify more, you really want to think about what cotangent is the same as, and we can see that's the same as cosine over sine. Oh, and look, and sine of theta is actually on the numerator and the denominator, which can cancel out. So in all, this basically just simplifies out to a nice simple cosine theta. So that's how we simplify expressions. We look at what identities can we use, and then from there, try to see what can cancel out and just simplify along the way. Number 8, secant x minus 1 times secant x plus 1. Now, right now, we actually don't have a property that we can use outright. If you recall from one of our previous pages, we have some of these identities, right? And the idea being is maybe we can do something with this, right? Like a secant. Notice that this is using a secant squared, though. So you'd want something like a secant squared minus 1, or something along those lines, maybe using a secant squared. Currently, we don't have that. We just have a secant of x. So you might actually have to do a little bit of just regular algebra here. Think of this more like an a minus b times an a plus b type of situation. What you can do is just multiply everything through, distribute everything. And so you'd end up with secant squared of x plus a secant of x. Then we get a minus secant of x. And what you'll see there is that, the outside and the inside terms basically cancel each other out, right? And then we have a minus 1 as well. So what we have now is a secant squared x minus 1. And so this is where you want to think, oh, what are my trig properties? And if you ever forget, you can always just jot them down off to the side and think, how can I establish some of these properties, right? And if I want to get like a secant squared, the idea is that I want to have that 1 over cosine squared. So maybe I should be dividing everything by cosine squared. If you don't have your trig identities quite memorized yet, then it's just as simple as doing it on paper, just like this, just off to the side, so that way you can really get the idea that what you want to find is what you see here, that secant squared minus 1. And so secant squared x minus 1 is really the same thing as saying tangent squared of x. So that's going to be our simplified version, just tangent squared of x. Okay, so that's the idea behind simplifying. Basically, modify the expressions as much as you can, see what identities you can use, and then cancel things out along the way. And then hopefully you'll get down to something as simple as what you see in these two examples here. Okay. All right, going on to the next page. We're now going to be proving identities. So as we prove identities, it's a little bit different from simplifying. The idea being is what you want to first do. I'm going to go through the general process here. The general process is, first thing you want to do is figure out which side is more complicated. Okay, which side is more complicated? And typically when you see something like in example number 3, complicated sides typically end up being sides with fractions, right? So you want to look at what is going to involve the most work, and that's what you want to kind of work with. So in step 2, once you have identified the complicated side, you're going to start by writing that complicated side, and then you're going to set it equal to, and then you're just going to leave a blank, okay? You're going to write that complicated side, and what you're going to do is you're going to end up simplifying just that side. Just that side. And you leave the other side alone. Leave other side alone. Because that other side, it really just acts as your answer key. You don't really want to pay attention to it, really. So what I mean by that is, as we take a look at example 3 here, as I examine the left side versus the right side, the left side looks a lot more complicated. So what I'm going to do is just kind of leave this alone and just push it away, tuck it aside. Don't look at this. Don't look at this. Okay, so we're gonna close our eyes and not look at this side here. What we're gonna do is we're gonna look at this side right here. Okay, so we're gonna look at this side. Okay, so we're gonna write down the left side, cotangent x minus tangent x over sine x cosine x, and we're gonna set it equal, just like that. Okay, so that's step 2. Write the complicated side, set it equal, and now comes the part where you just simplify. Okay, so thinking about how we did the last 2 problems, just think, okay, what can I do here? You have a variety of options here. There's really no one wrong way to do these kinds of problems. Some people like to look for identities. Some people like for instance, using like sine squared plus cosine squared. Remember that we also had like a 1 plus cotangent squared or a 1 plus tangent squared, anything like that. If you don't want to work with identities, you can also just go with a plain and simple way of saying, hey, if I see a bunch of trig functions, I just want to keep it as simple as possible and keep it all maybe in like 1 or 2 trig functions, which means if I see tangents in here, what I could do is technically just turn everything into sines and cosines. So for instance, if I see cotangent x there, I could change that into a cosine x over sine x minus, and then tangent is the same thing as sine x over cosine x. So you'll see that everything is really just in terms of sines and cosines. And that's also a perfectly viable way of working with these proofs as well. Okay, so you don't have to be looking for like identities. You could really just turn everything into sines and cosines if it fits. Okay, so since we've already done this process, let's go ahead and go through this. Now, since everything's in sines and cosines, and what I see here especially is that I see that I have fractions that are trying to be combined together. What leads me to want to do here now is try to get those as common denominators. And so the way I can get common denominators then is I see that the first fraction would need a cosine, and then the second fraction would need a sine. So keeping that in mind, what I would then see here is that I end up getting a cosine, and then because I would have to multiply the top by cosine as well, I really get cosine squared x minus, and then here, because I have to multiply by sine x again here as well, I get minus sine squared x. And then because I am combining fractions and they all have the same denominator, remember when you combine fractions, you can actually put them under the same denominator of sine x cosine x. So everything that I have in purple here represents everything just in the numerator. Okay, that's all of this piece here. Okay, but I cannot forget that I also have this over the denominator of sine x cosine x. Okay, well, is that confusing to you? We have a fraction divided by a fraction. If that is confusing for you, then of course you can always rewrite this. Remember that a fraction divided by a fraction is the same thing as a fraction multiplied by its reciprocal. So that's what I'm going to do. I'm going to change this so that what we have is the numerator, cosine squared x minus sine squared x over sine x cosine x. That was my first fraction, the purple that you see up above. And then I had to multiply that by basically 1 over sine x cosine x, just like that. Okay, and that represents the denominator that you see up above as well, right there. Okay, so now it's time for me to figure out, okay, what can I do here? Well, I have cosine squared minus sine squared. Notice how the sine x and cosine x are also the same types of terms. They're all being multiplied together. So I could rewrite this as cosine squared x minus sine squared x over sine squared x cosine squared x, since I'm just multiplying everything together on the denominator. And then when it comes to fractions, I don't have a whole lot of space here, so I'm just going to kind of create a little scratch pad in this area again. You know, when you have something like, I'm going to give you a little brief example. Let's say 3 minus 2 over 5. really that can be set up as 3 over 5 minus 2 over 5, right? You're just kind of separating those fractions apart, and that's kind of what I see here. I can separate these fractions apart to give me cosine squared x over sine squared x cosine squared x minus sine squared x over sine squared x cosine squared x. And from here, you'll notice that I actually have common terms on top and bottom that can be canceled out. Right? And what ends up being left over then, sorry, I don't have a whole lot of space here, it's equal to 1 over sine squared x minus 1 over cosine squared x. Now, what is 1 over sine squared x the same as? This is going back to our original problem. This, remember, is kind of like our answer key. What we want to establish is this identity here. Well, 1 over sine squared x is the same thing as cosecant squared x, and 1 over cosine squared x is really the same as secant squared x. So right there, now we have found it. We have figured out the right side of our original problem. Okay, so that's basically all there is to proving identities. You're just taking one side, and then by the end of simplifying it, you should end up getting to that last side, the other side. And that's really what you're doing in these proofs. Okay, so when you're doing the proofs, just keep in mind what side looks more complicated. Just work with that side, and by the end, you should just get the other side. But you should not just try to cheat your way and just say that, oh yeah, I got the other side, right? You want to actually figure out, how can I simplify that expression to actually get the other side, okay? So it's basically like just having an answer key right in front of you rather than having to turn to the back of the book. That's all proofs really are here, okay? So we'll stop the lesson here.